Today's topic is about marginal and conditional distribution. Marginal and conditional distribution, or marginal or conditional density, are interconnected to one another. Okay, so in today's class, I shall first discuss what is conditional distribution or conditional density, and after that I'm going to discuss what is marginal distribution or marginal density. And once we get the idea of these entities, then I'm going to discuss two problems related to these topics of today's class. So let us begin with conditional distributions definition first. But those who have joined, I am requesting all of you to keep a copy in front of you so that you can write the expression of the formulae, which I'll ask you to write because whenever I shall be scrolling down, then you can refer to the formula written on your copy to my problem, which I'll be sharing with you. So you just it's just a homework. Okay. My first definition goes like this, that if now before I start, I must tell you one thing. So many notations have been used in this particular note. Okay, now if you can compare the note which I shared with you, you will find that there I wrote fxy, and here in this place I wrote so far as I can remember, I wrote gy. Okay, now notations, you can use many notations. Several people may use several notations. There is no universality in applying the notations, but notations will make troubles when the content is not clear to you. But if the content of the topic is clear to you, then the notations will not be making any troubles. You can use any notation. For my sake of understanding, or you can say from a pedagogical point of view, I have used this notation. I have changed the notation to this. Okay. Here I am writing that small f is denoting the function. The small f is a function of how many variables? Two variables. So I'm writing here x comma y. These are the variables. And this small x is the value of the corresponding random variable capital X, which has been written in the suffix. Small y is corresponding to the random variable capital Y, which is written in the suffix. So therefore this notation, f of xy of x comma y. Okay, mother variables are written in the suffix, and the siblings have been written as the values, the variables inside the function. And here also you see, since it is a function of single variable only, I have written y here, small y is a value, and it is the value of the corresponding mother variable capital Y. Okay, so I have written f capital Y of small y. So this, that is how we have used the notation over here. Now the definition goes like this: if fxy is the value of the joint probability distribution of the discrete random variables capital X and capital Y at xy, and f capital Y of small y is the value of the marginal distribution of capital Y at small y, the function given by, look at the notation, what I have written, a function which is a function having the values as this. The function is having the domain values as this. Small x is given, small x given that small y, x given small y. This is the shape of the value of the function. And these values, you know very well that these values correspond to the mother variable capital X given capital Y. So it is actually defining the condition imposed on the variable. The condition says that the variable, mother variable capital Y, has already considered the value small y. Given that this, we are supposed to find the probability that capital X is going to take some values. And you know very well the definition of conditional probability. So that notation has been used over here. Now, if I can recall the definition of conditional probability, it is defined like this, that if capital A and capital B are two events, then probability of A intersection B, probability of A given B will be probability of A intersection B by probability of B. Okay. Now here, since I am supposed to find that the mother variable capital X is going to take a value small x, given that capital Y has already consumed the value small y, that will be defined as the joint probability of the two variables as written in the numerator divided by the marginal probability corresponding to the variable y. Okay, look at the expression and you write it in your copy. So this is the expression. This is known as, this particular formula is known as conditional distribution of the random variable capital X, given that capital Y has already taken the value small y. Okay, so that is the definition of conditional distribution. Here is one particular condition is, extra condition is also there, which is pretty obvious. It is that the denominator term must be non-zero, otherwise the definition will collapse. Okay, now similarly, if I don't if I don't tell you anything, what? Somebody has written something, let me check. Sir, I was present the previous day. Somebody has written that, sir, I was present in the previous day and due to network problem, I was unable to connect myself for a long time, maybe. Why might? Now, those who have written this, who has written this? Ayushi Mukherjee. Okay.
Sir, yes, sir.
Okay, okay. So you write your roll number, then I will rectify that. Always write your roll number.
Okay, sir.
Okay, okay. Not to worry.
Okay, sir.
Now this in conditional distribution, that in conditional distribution, there is one extra condition that the denominator term must be non-zero. Okay, otherwise the definition will collapse. Similarly, you can build your definition of conditional distribution of the variable, random variable capital Y, given that capital X has already consumed one value, and that is defined as this: f of capital Y given capital X of the variables of the form small y given small x is equal to joint probability of the two variables divided by marginal probability of the variable capital X, given that the denominator is non-zero. Okay, so these are the two definitions of conditional distribution. Now in the next part, I'm going to modify the distribution a little bit. Modification will not be a huge, a little bit of modification will be there. So you just see what is happening. I am now terming this thing, which I have written here already. I have copied the same thing over here. You see, carefully observe the portion marked blue and the portion here marked green. They are same. They look very similar, and they are similar. But after that, I have mentioned that your small x is having the values from -infinity to +infinity. Small x's range is specified. Here, the small x has not been specified. Here, the small x is specified. When small x is not specified, I am calling this as conditional distribution of capital X given capital Y equals to small y. But when small x is specified, I am terming this as conditional density of capital X given capital Y equals to small y. So both expression wise, both of them are same, but their names have changed depending upon whether you are specifying the domain of the variable capital X or not. Similarly, just like this, if you denote this as conditional distribution of capital Y given capital X equal to small x, here the range of the domain of small y has not been mentioned specifically. Then if you mention it specifically, as I have done here, that y is taking the values -infinity to +infinity, then you see the portion marked blue here and the portion marked green here, they are similar with respect to their expressions. But since y hasn't been specified, so the domain of y hasn't been specified, so I'm just calling it as conditional distribution of y given at capital X equal to small x. And here, since y has been specified, I am terming it as conditional density of capital Y given at capital X equal to small x. Now, which is the working formula? Which particular formula should be our working formula? Is it that one or this one? Is it that one or that one? Okay, the answer is always use the formula, or make sure that you are actually using not this formula but that formula, because here the variables domain are specified. If the domain, since we are dealing with functions, and since if the domains are not specified, then you cannot say that these formulas are actually working formula. Okay, so my working formula is this green colored formula. Remember this. So we shall work with conditional density of this form and conditional density of y of this form. Even if they are similar, I shall keep in my mind, in the back of my mind, it will always play that I'm using these two as domains of x in the first one and domain of y in the second y has been specified clearly. Okay, so this is the formula of conditional density. Now in conditional density, in both these cases, two things actually appeared. One thing is this marginal density of capital Y, and another is marginal density of capital X. Now, what do we mean by marginal densities? Okay, we have to be very clear about that. What is marginal density? So my next question is about what do we mean by marginal distribution? All of you, those who are attending my today's class, you all please quickly copy this particular table in your copy. Okay, because I'm going to scroll down. This particular table is the joint probability distribution, which we have already calculated in one of our previous classes. I'm referring one of my previous videos on bivariate distribution, probably the first video, not the second one. We have already calculated this. Okay, I am again referring this particular joint distribution over here with one extra column added and with one extra row added. And what are these columns and rows containing in them? Let us discuss. This is my actual point of discussion in today's class. So if this is my probability distribution, joint probability distribution, I am reforming the joint probability distribution by attaching one extra column and one extra row to it. Just remember one thing, in matrix, we have the tendency to write small x on the left and small y on the top. But here, I have changed it because I wanted to show you that this is not actually universal here. You can write small x here and small y over there. You can interchange their positions. It will not affect your probability, but you have to be careful enough that in which particular cell you are putting which probability. Okay, so if this thing is clear to you, whether you write y on the top or y on the left, that doesn't actually affect our calculation. Remember, in this particular scenario, I have put small x on the top and small y on the left. And these are my extra columns, and this is my extra row. What are these? This is nothing but, you can check by yourself. If you take the sum total of these numbers, 1 by 6 plus 1 by 1/3 plus 1/12, that will lead you to 7/12. If you add the numbers 2/9 plus 1/6, that will add to 7/18. And since only one probability is there, 1/36, then that will lead to 1 by 36. Okay, so these are the sum total of the rows. Similarly, 5 by 12 half and 1 by 12 are the sum totals of the columns. Okay, now why am I showing this particular example to you? It is because I'm going to tell you what marginal distribution is. Now marginal distribution, you see, let me show you from the chart first of all, that this entire thing, in its entirety, the numbers which are written, the probabilities which are written inside the rectangular box, they are joint probabilities. But the probabilities which have been written outside the box, on the column or on the rows, these probabilities are called marginal probabilities. These probabilities corresponding to joint probability distribution. These probabilities correspond to marginal probability distribution. So the probabilities lying outside the rectangular box are known as marginal probabilities. Now, which one is the marginal probability of y and which one is the marginal probability of x? The thing which is coming row wise means this one. These are called the marginal probabilities of y, and these are called the marginal probabilities of x. because you are getting these values by taking the sum total of x's values. You are getting these values by taking the sum total of the y's values. Now, when you are calculating the marginal probability of y, then you are taking the sum with respect to x. You see, you are varying x on the function. You are putting x equal to 0, you are getting this value. You are putting x equal to 1, you are getting this value. You are putting x equal to 2, you are getting this value. But the ultimate product is not the marginal distribution of x. The ultimate product is the marginal distribution of y. Similarly, when you are calculating the marginal distribution of x, then you are varying the variable with respect to y. When you are putting y equal to 0, you are getting 1 by 6. Then you are putting y equal to 1, you are getting 2 by 9. Then you are putting y equal to 2, you are getting 1 by 36. And so by taking all the values of y and summing it to joint probabilities corresponding to the variable y and summing them together, you are getting not the marginal distribution of y, but marginal distribution of x. So in calculating marginal distribution of y, we need x. In calculating marginal distribution of y, x, we need y. Okay. Now that thing will be expressed in a general sense below. Now you'll understand what is happening. So if we take the capital X to be discrete random variable, taking this value 0, 1, 2 as in the above case, you see that we have calculated the marginal distribution of X with respect to Y. The sum has been, the joint probabilities have been added together with, and the Y, the variable Y has been varied from 0 to 2. And when we are calculating the marginal distribution of y, when capital Y and X are discrete, we have what we have done. We have varied the values of X from 0 to 2. And we have added the joint probabilities together. 3 values of X's are there, so 3 joint probabilities, and the sum will give you the marginal distribution of Y. So these notations are very important. I'll ask all of you to please be attentive and note it down carefully, because that will be very applicable to our problems of marginal density, and we have, the idea must be clear to you. Now, so far as I can remember, in the note which the partial note which I shared with you in the last class, because I couldn't take the class, I told that, and I couldn't take the class and my class got cancelled because of this unforeseen event. This particular expression was written as gx, and this particular expression was written as hy. But I shall ask all of you to stick to these notations, because these notations are too explicit to represent what we are actually talking about. Okay, now that is our remaining, whatever expressions you are comfortable with, the definition of the expression must be clear to you. So the definition now goes like this. I'm reading it out once again for you. The definition says that if capital X and capital Y are discrete random variables, and f capital XY of X comma Y is the value of their joint probability distribution at the points XY, the function given by this summation form, marginal distribution of X summation over Y for each X within the range of X is called the marginal distribution of X. Correspondingly, the function given by this Fy, marginal distribution of Y summation over X for each Y within the range of capital Y is called the marginal distribution of capital Y. Okay, this is for discrete case. We have already understood what discrete case is. For continuous case, the same thing will be written. You already know, you have the idea already that in continuous case, the summation is replaced by integration. So we are integrating. When we are calculating the marginal distribution of capital X, we are integrating the function, the joint probability function, from minus infinity to plus infinity. And when we are calculating the marginal distribution of Y, we are integrating the function joint probability. Remember, students, since I'm typing the notes, sometimes there are some printing mistakes. Okay, so I beg pardon for this type of mistakes, silly mistakes. I must not do, but you rectify this thing. Okay, so you see, I have missed the suffix over here. See, I am moving my cursor. I have missed my suffix. I have not written capital X comma Y. You please don't get confused, because this type of activities by teachers always make students very much confused. Okay, so I beg pardon, I have missed it. So before sharing the note, I will rectify. You just put capital X, Y over here. In mathematics, this kind of mistakes are unpardonable. So f of this suffix will be there always. Okay, so you keep it in your mind. So while calculating the marginal distribution of capital Y, marginal distribution of the random variable Y, we are integrating with respect to X. And the integration is from minus infinity to plus infinity. So these are the marginal distribution. These are the definitions of marginal distributions which have been used in the definition of conditional density of the random variables capital X and capital Y. Now, after this, here is a problem for you, problem number 1. But before I discuss problem number 1, I shall discuss problem number 2. I will tell you why I'm doing so. Because in problem number 1, is actually not having the, in problem number 1, we didn't calculate the conditional density. Conditional density was absent. In problem number 2, here is a problem for you where conditional density and marginal densities will both be calculated. Once I make you understand what problem number 2 is saying, I shall go back to problem number 1. Okay. Now, you quickly write down the expression in your copy. You don't have to copy the entire question. The joint probability density function for the continuous variable is given in this particular form. F of capital X, Y of X, comma, Y, F suffix capital XY of X, comma, Y is 4xy when small x is lying between 0 and 1 and small y is lying between 0 and 1. And when x is having any other values outside this range, the probability is 0. Not only x, if x and y are jointly having any values outside this range, the probability is 0. We are going to calculate the marginal densities of capital X and capital Y. Also, we are going to find the conditional density of capital X given that capital Y equals to small y. Now, marginal density of capital X by our formula, which we have already discussed, is calculated in the following way. To calculate the marginal density of capital X, we integrate the integrand in terms of y. And the y is ranging from minus infinity to plus infinity. I have just applied the definition. Now, you already know from your previous experience of probability distribution that what we do after that, we divide the limits into several halves. So we can write the limits as from minus infinity to plus infinity, minus infinity to 0, 0 to plus infinity. Sorry, minus infinity to 0, 0 to 1, and 1 to plus infinity. But this step is not shown actually because it is obvious, it is implied. So we know this joint probability is only defined when y is lying between 0 and 1. So I am putting only this limit over here. So minus infinity and plus infinity have been replaced by 0 and 1. When we integrate, since this function contains both x and y, but we are going to integrate with respect to y, so the term x will be treated constant. So there will be no change in the term x. Okay, you already know it from your previous experiences. So we will write it as 4x into y squared by 2. Y is running from 0 to 1, and which comes out as twice x, where x belongs to 0, 1. Okay, now we write this joint probability, we write this marginal probability of x in this function form. That fxx is the function which takes the value twice x when x is lying between 0 and 1, and it's 0 when x is outside this defined range. Similarly, the marginal density of y is calculated as f of y, where the integrand has been integrated from with respect to x from minus infinity to plus infinity. Okay, now again, the function is defined for x equal to 0 to 1. Now we have put the limits here from 0 to 1. Okay, and we have integrated by considering the variable y constant. So we get 4y into x squared by 2 from 0 to 1, and the result comes out to be twice y. And we're writing the function in the following form, that fyy is equal to twice y when y is lying between 0 and 1, and 0 elsewhere. Okay. Now, once we got these marginal densities and for capital X and capital Y, we are going to calculate the conditional density of capital X given capital Y. We can also calculate the conditional density of capital Y given capital X. But in the question, we are supposed to find this conditional density. So I'm showing you this calculation only. Okay, but you can do the opposite also by yourself. So conditional density of capital X given capital Y is calculated as, apply the formula. Oh, students, one more thing. If you stick to the notation, if you like to stick to the notation, you must write in the suffix capital X given capital Y. So it's my mistake not to remain consistent. Okay, so I shall rectify this. So so you must write here that in the suffix that it is the random variable, the mother variable here is capital X given capital Y. Now if we do this, what we'll write, we will its formula is given as joint probability of XY given by marginal distribution of Y. Okay, now joint probability of XY has been calculated as 4XY and marginal distribution of Y is calculated as twice Y. And now from this calculation, we get this to be twice X. Okay, so we have got this conditional density of X given Y is as twice X. It is written here in terms of the function. So this is my conditional density function as has been calculated. So this is the application, direct application of the problem, direct application of the definitions which I have discussed above. And this definition corresponds to the continuous variable. You can do the same thing corresponding to the discrete variable case. Let us now go back to the problem number 1. The problem number 1 says the same thing, a joint probability of in terms of X and Y is given to here. You note down this in your copy. It is Cx plus 1 and X comma Y greater than or equal to 0. And there is one extra condition, that is X plus Y less than or equal to 1. There are certain jobs to perform over here. First job is to find the range of the mother variable capital X, pair of random variables capital X and Y in the XY plane. Okay, so let us first do it. Now students, you know that in the previous class I have explained to you that we actually consider a three-dimensional space. Okay, when we talk about double integration, we consider the three-dimensional space. And in three-dimensional space, what we do, we vary the variable X on the X-axis and we vary the variable Y on the Y-axis. Okay, and we get a rectangle, square-shaped thing, square-like thing. So we get a square-like thing on the base. Okay, we actually mark its area. Okay, I showed you in the last class. And on this particular area, on this particular thing, we erect the function. Now, the function has some kind of height. And when we multiply the height by the area of the base, we get the volume of the object which we erect. That is the geometrical interpretation of double integration. So here they are asking you to note down the range of the mother variable X comma Y. So in the XY plane, and you see that range will be like this. I have drawn this particular figure. This is the figure. Since X is greater than 0 and Y is greater than 0, positive quadrant has been chosen. And since X plus Y is less than or equal to 1, X plus Y equals to 1 is a straight line. This is the straight line represented by X plus Y equals to 1. But remember, if a linear equation represents line, then the inequation represents the region bounded by the line. Now, it is a question for all of us that whether this portion will be will represent X plus Y less than or equal to 1, or that portion will represent X plus Y less than or equal to 1. That can be easily judged. The way is, whenever you get an inequation, you put the origin values with respect to the variables. You put X equal to 0 and Y equal to 0. Now, if this satisfies the inequation, then the region will be that side which contains the origin. But if after putting it doesn't satisfy the region will be just the opposite side to that side which contains the origin. So suppose I have x plus y greater than 1. Now you put x equal to 0 and y equal to 0. 0 greater than 1 is absurd. Now x plus y, this line will remain same. But 0 is not satisfying the equation x plus y greater than 1. And therefore, the region corresponding to that will be that region opposite to the region containing 0, 0. So in that case, my region will be this one. Okay, that is how we mark the region in case of inequalities. So here the region will be this, Rxy will be this. Our next job is to find the constant C. To do this, we apply this formula, minus infinity to plus infinity, double integration fxy dx dy equals to 1. And we integrate. We integrate by, I have already shown you how to integrate this kind of functions. Okay, I have here first integrated the function with respect to y, and then I have integrated with respect to x. But there is no any hard and fast rule. Okay, if you can change the nature of the integration, then you can integrate with respect to x first and then with respect to y, which I have done below. Okay, so that you must not confuse yourself that this should be with respect to this problem. If you interchange the integration, then also the result will be the same. So what we do here is that we are going to integrate the function from 0 with respect to y first. Now you see, x is having the region. Now since x plus y less than or equal to 1, therefore x is lying between 0 and 1 and y is lying between 0 and 1. Okay, and therefore, since x plus y is less than or equal to 1, from there I can write that y is less than or equal to 1 minus x. Now already we know that y is greater than or equal to 0. So y's range is this one. Okay, so y is lying between 0 to 1 minus x. So I have written here, y is having the value 0 to 1 minus x. Okay, I'm putting the integrand and then I am integrating with respect to y first and then with respect to x. And after that, this simple calculation, we get the variable constant's value as c. So my function is actually becoming 3x plus 1 with respect to these conditions. Okay. Similarly, you can do this calculation by yourself by integrating x first and then with respect to y, and you will get the same result. Here you have to keep in mind that x will range from 0 to 1 minus y. My third part of the problem has already been done by in this particular class in problem number 2, that to find the marginal distribution of the random variable capital X and marginal distribution of the random variable capital Y. So I am not explaining these calculations to you because that has already been done and you will definitely understand. Okay, you will definitely understand. So these are the marginal distributions. Now I have calculated this. You go through these calculations. You will find you can do it by yourself. That this particular part of the problem has already been explained in the previous problem. Now the last problem, I am considering this one. We are going to find the probability that y is less than 2x square, for which I am considering this figure. Okay. Now this is your x plus y equals to 1 line. And y equal to 2x square is the parabola. This is the parabola, but this is the partial, the one half of the parabola on the positive side. And I'm considering on the only the positive quadrant because x is greater than 0, y is greater than 0. And this parabola is cut, this half of the parabola is cutting the line in this particular point, at this particular point. And if you solve this, you will find the coordinate of the point to be half, half. Now y less than or equal to 2x square, that region will be represented by that portion. You substitute the origin, you apply the same formula of origin, and you will find that that portion will be represented by y less than or equal to 2x square. Not only this, x plus y less than or equal to 1 and y less than or equal to 2x square combined together will give you this intersection point. So this is the common feasible region. Okay, after this class, you just do a little bit of mathematics, you will understand. Now we are going to find the, we are going to vary my variable x and y in this particular region, and we are going to integrate to calculate the probability. So what have I done? First of all, we have written the original formula, And then we are integrating the integrand with respect, we are first integrating the integrand with respect to x. Now the function has taken the form 3x plus 1. And the after that we are integrating with respect to x, but x will vary from 0 to 1. What will be the variation of y? Now y will vary, its lower limit will definitely be 0, and its upper limit will be the minimum of 2x square minus 1 minus x, because it is the minimum point. This is the minimum point, and therefore we have considered this minimum of 2x square comma 1 minus x. That will be the upper limit. Okay. Now when we integrate this with respect to y, we get 3x plus 1 into y. We are putting the limits over here in this manner, and then we are breaking this into two halves. If you observe the figure carefully, you will find that from 0 to half, the x value will be 2x square. Okay, the function will be 2x square, and from half to 1 for x, the function will be 1 minus x. And that is how we calculate the probability, and it comes out to be 53 by 96. You go through the problem once again. If you don't understand, you can again ask me in tomorrow's class. Now the time has already running out, so the class will get cancelled. So hope so you've understood so far, and bye for today. We'll see you tomorrow, and if needed, we'll discuss this once again. Okay, so tata. I have saved all the chats.